All right, there we go. Just getting, of course, always a few last minute changes to make. All right, let's actually get started. Welcome to our second class back after the midterm. I will have a bit to say about the midterm stuff. You've now seen your grades and your rank in the course. And then the post I saw about final exam replacing midterm scores stuff. I'll talk about all that. And then we will do just a quick recap of the exponent rules that we talked about last time, but most of today is going to be talking about sequences and series. So starting to talk about these. Okay, so some little announcements. I think all of your professors have been telling you about this like violence prevention video thing. I'm pretty sure it's like a training thing sort of made by the governments and then sort of passed to the schools, and told that our students need to watch it. So hence professors telling you. So just do that. They're just videos. So like turn it on while you're eating lunch or something. You can just kind of watch. So there's that. So please make sure you've done that by Saturday, the 30th. Just 3 more days. So by the end of Saturday, that needs to be done. Course evaluations. Also, you have until Friday. Yes. So tomorrow at like, I don't know if there's an exact time for the deadline, but just do it today. For all of your courses, I know I gave you that survey, but that was my own survey with extra questions and like my own particular things I wanted to ask. There's a more general course evaluation for all of your courses, which you should do like now, like today on the SAIS websites. If for most of you are first semester students, so you might not be aware, but if you don't do these course evaluations, then you are not able to view your final grade sort of in the standard viewing period. You'll see it a few weeks later than everyone else. So make sure you have completed your course evaluations for all the courses that you are registered in. All right, so just little announcements about that. Midterm, let's talk about this. So I posted your score. First, there were some questions about that, which sort of realized after the fact could have been a little clearer. I've reported your score to you as a number out of 20. That's because in the weighting of our course, the attendance counts as towards your overall grade. Attendance counts as 20, homework counts as 20, the midterm counts as 20, and your final exam counts as 40. So that's the kind of breakdown. So the midterm score out of 20 was that. So that's the number that you saw there. That's how you can interpret that. The average was about 56%. 56, a little different for each class. So not especially high, definitely. So a few things. First of all, if you scored well below the average, I would strongly recommend that you come talk with me. And I definitely want to talk with you and talk about how the midterm went, why it may have been more difficult, if you were preparing, if you felt you were well prepared, but then still the exam was quite difficult for you, then let's talk about all that stuff. So strongly recommend that you schedule an office hours meeting with me. Second thing, ranks. So your overall rank in the class, I'm sure you are aware, but there's a kind of limited number of A's and B's that can be awarded. So your rank will let you know sort of where you stand relative to other students. So remember that the average on the exam was about 56%. So were you above or below that average? And if you see the rank, out of your section has like 50 something, 56 students registered, I think 57. Trying to remember the exact number. It's on the Google Classroom page. You see a number out of that 50 something. So you can get a sense of where you are. Are you kind of in the top half, the bottom half, or like the very top, or whatever? Third thing, because these grades were lower, I do want to give you another chance on this. And this is not all, but a lot of math classes, my math classes when I was a student were like this. Your final exam score, if as a percentage, whatever that is, if you do better on the final exam than you did on the midterm, then the final exam will become larger. So instead of 20 for midterm, 40 for final in your overall course grade, it would become 0 for midterm and 60 for final. So the final just kind of absorbs that. So if you do better on the final, I'll just forget the midterm score and just use your final exam score. If your midterm score is high and then your final exam score is not higher, then okay, you just kind of keep the 20 and 40 as is. This is done on an individual basis. So for each student, I will do the thing that gives that student, you, the higher grade. So it'll be different for each person. It's not like everyone in the class together or something. Okay, so that's the opportunity here. If you're not satisfied with your midterm grade, you have a chance to make it just disappear by doing better on the final exam. I wrote more detail and more explanation and stuff about this on the classroom page, but I want to give you an opportunity right now to ask questions. Does anyone have a question about this kind of policy here?
Sorry, Professor.
Yeah.
Like, you erase your midterm score. We have to erase it like literally, or?
No, it just, this is what I mean. If your final exam score is higher, you do better on the final exam than on the midterm, then your midterm will just not be counted towards your overall course grade. Only the final exam will be counted. That's the erase part.
Thank you, Professor.
Other questions? You guys probably have some more questions about your individual circumstances. You can ask that at the end of class. For now, one more thing. I did get messages from 1 or 2 students saying like, oh my God, am I going to fail? Do I still have a chance to pass the course? For nearly every single person, the answer is yes. Final exam that's worth 60 points out of 100 in your final course grade. That's really big. So kind of anything can happen with that. It does require that you do better on the final exam than on the midterm, but there are the only people who are at serious risk of failing currently, like have no chance, they're the people who didn't come to the midterm at all anyways. So if you're here and you're listening to this, this is almost definite. That's almost definitely not you. Okay, so let's go on. Exponents, we'll do a bit of quick review here. So I showed you these lots of different rules here. These 12, listed as 12 there, but we have 13 here. 13 different rules. The ones, if exponents are a little maybe trickier for you, they're probably just 5 that you need to kind of memorize. The rest should sort of naturally follow, should be intuitive from those. So remember that a fractional exponent is a root. A negative exponent means we flip over the thing, it becomes an inverse. If we have the same base multiplied together, then you can add the exponents. If we have the same base and it's an exponent to another exponent, we can just multiply them. And if we have the same different bases, but same exponents, we can, that's just factoring. Factoring works the same as everything else. So we can still factor with exponents. Okay, so vocabulary, we talked about this last time. A whatever to the exponents, whatever. And if we're talking about roots, then an nth root of something, some special term, squared, square roots, cube, cube root. Okay, so sequences and series. This is our next 2 or 3 classes are about this. So arithmetic, some basic types, and then geometric, which most of you have seen arithmetic before. Geometric, maybe not everyone, and then we'll apply that to interest rates and see how these directly work at interest rates. Not today, but more, not tomorrow, next class, Tuesday, we'll talk about this notation. If you've never seen this style of writing a sequence before, we'll get to that, but we'll get to that in the next class. Okay, so just basic definitions for anyone if it's been a while. A sequence is a list of numbers which follow some, just any kind of list, and there's some sort of pattern or rule to the list, whatever that pattern or rule could be. And then any part of the list, we don't call them numbers, we call them terms. So first term, let's say we call it A1. Then the second term is A2. Third term is A3, A4, etc. A generic term is just AN. A and N is whatever number, it's 5 or 10 or 1 or something. So we don't call these numbers in the sequence, we call these terms. So one important word to know here. So term, general term, AN. So let's just take a quick look at how these are rather similar to graphing, and then we'll move on to, or we'll actually look at some sequences directly here. So let's look on the left here. If we had a table of values, so f of x equals 2x or y equals 2x. We did lots of graphing with stuff like this. So let's say we have a line. 2x would be a line that looks roughly like this. So when we draw these lines, it's kind of a solid line here. So let's try just make a quick table of values, x and y here. And when x is 1, 2, 3, 4, 5, 6. All right, so for this function here, y equals 2x, when x is 1, what is y?
2.
It's 2, because we are just doing 2 times 1, just substitute in the value, and then of course that's 2. When x is 2, it's 2 times 2, which turns into 4 and 6 and 8. So very clear, not hard to calculate here. So when we make a table of values, these are each points here, of course. So point 1, 1 comma 2 points 2 comma 4 points 3 comma 6, like this. So we have these points, but then we connect all the dots. We connect all the points and we make this sort of solid line like this. For a sequence, we do a similar thing, except we kind of don't usually connect the dots. So let's say we make a table of values for this sequence here. And we have n here on the left, and then we have an here on the right. So the first term of this sequence, what is it equal to?
2.
It's 2, because we define the terms as 2 times n, so 2 times 1 equals 2. And the second, go do a few of these. Second term, 2 times 2, so 4. Third term, 2 times 3, which is 6, 8, 10. So very simple pattern here. But when if we are to put this on a graph, which let's do this. Move this up. Make a new graph here. We kind of just draw the dots. So here's 0.12, here's 0.24, and 3, 6, and 4, 8, and 5, 10, etc. So we just kind of care about the main points. We don't really try to, for a sequence, we don't calculate, well, what is our a value when n is equal to 2.3 or 4.7 or something. Like, we don't do that, we just stay with the whole numbers. But aside from that, it's pretty similar to what we were doing with the graphing. We could make a graph for any of these sequences. We usually don't, but still, in this case, we're still working with a linear relationship. Okay, so that's just a connection with what we were doing in the past for our midterm. So let's just actually build some sequences here. So let's say we have on the left this thing. So our general term an is equal to 4n minus 3. So let's try to write the first 5 terms of this sequence. What is the first term here?
1.
It's going to be 1, we say. All right, so it's just, we can, if we want to verify this, we can just write out some math here. So a1 is equal to 4 times 1 minus 3, 4 minus 3, okay, 1. What's the next term?
5.
5. We can check that one too. A2 equals 4 times 2 minus 3. That's equal to 5. Okay, what's the next term?
9.
9.
Okay, 9. We can write this out. 3, 4 times 3 minus 3 equals 12 minus 3 is 9. Once we've done at least 3 terms, usually the pattern will become very obvious. If we want to be like really certain, we could just do one more. 4 times 4 minus 3. Okay, that's going to be 13. Okay, we see a pretty clear pattern happening here. So we shouldn't need to manually calculate the next term. We can just kind of see it. So what is the next term?
17.
17. Okay, tell me the next three terms.
21,
21,
25, 29.
Okay, so we see the pattern, right? We're just adding 4 each time. Once you have at least 3 terms, usually the pattern is very clear. You can stop manually calculating and just write them out. Let's do another one here where the pattern will look a little different. What is the first term of this sequence?
3,
3. Okay, what's the next term?
5,
5. Okay, what's the next term?
9,
And the next one?
17.
17. Okay, let's check these. So A1, we say it's 2 to the exponent. 1 plus 1, that's 2 plus 1, that's 3. A2 is equal to 2 to the exponent 2 plus 1, that's 4 plus 1, that's 5. A3, 2 to the exponent 3 plus 1, which is 2 cubed, that's 8 plus 1 is 9, etc. Okay, we get the same thing, 17. And we kind of notice the pattern here. The next one's probably going to be 33. Actually, sorry, first 5 terms. Let's make sure we get that right. So 2 to the exponent 5 here. 2 to the exponent 5 is 32 plus 1, that's 33. Okay, so we see we have a different growth pattern here. This one, the one on the left just keeps growing by the same number, plus 4 each time. But this one on the right, it's a different growth pattern. It keeps, we did plus 2, but then plus 4, then plus 8, then plus 16, and we have a different pattern there. But for building a sequence, if we have a general term, we can just very easily use that to define any term, find any term in our sequence. Okay, let's go to our next ones here. So let's work backward. Let's say we have a general term, sorry, we have an actual sequence, an actual list, and we want to find the general term. So for this one on the right, what general term might work for this?
A plus 4.
It should be defined in terms of n.
Oh, sorry, n plus 4.
N plus 4, n plus 4. Okay, so let's try this. The way you were thinking of was a recursive sequence. It's another way of talking about them, but we're doing the simpler type here. So if we think this is right, we think we have the right general term, then we should test it. Test at least 3 of the terms and kind of make sure we have the right thing. So A1 would be n plus 4. N is 1 here plus 4. That would be 5. But the actual first term is 4. So doesn't look like this is going to work.
I would say 4n.
4n. Let's try that. So 4 times 1, that's not 5, that's 4. Okay, first term works, but that's not enough. We should check a few more. A2, 4 times 2 gives us 8. Second term is actually 8. Okay, that's working. Let's jump down to a different one. Let's try A5. 4 times n is 5. 4 times 5 is 20. Fifth term, actually 20. So looks like we got it. We've tested at least 3 terms. And kind of like when we did our graphing of straight lines, we tested 3 points or drew 3 points to make sure we had the right thing. So we can be pretty sure we have it right here. 4n looks like it's the right way to define a general term for this sequence. Let's do the one on the right here. So we have this pattern happening. 1, 3, 9, 27, 81, 243. Can someone suggest a general term that could work here? No one has an idea. Okay, so
I guess 3 exponent n.
3 to the exponent n. Okay, let's try this. So if we do this, we'd have a1 would be equal to 3 to the exponent 1, which is equal to 3. So that doesn't match our first term, but I'm going to write a few more of these, and then we'll see that we can just make a small change. Our second term, a2, 3 squared, and that would be 9, and a3 like this would be 3 cubed, which is 27. So this actually describes almost all of the sequence, except we're just missing the first term. Can we make a tiny change to our general term?
Maybe minus 2n.
Sorry, say the negative 2n?
No, it will be 3.
Mhm.
Like it's an equals 3. It's n, yes. Yeah, and minus 2n. No, not like this. Or like, yes,
Minus
2 multiplied by n.
minus 2n. Okay, this will give us something else. I would write out these terms and show us, but this is rather different. This is going to, you're overthinking it a little bit. There's a smaller change that we can make.
We need to make the exponent negative n.
Negative n. Negative n. That would give us a negative 3 and then a positive 9 and a negative 27.
Professor, 3 power n minus 1.
Okay, let's try that. Erase this stuff here. 3 to the exponent n minus 1. So if we do that, then these terms here are all going to be the same, except we just have a new first term. So this would be a2 would be 2 minus 1. That's at exponent 1. A3 would be 3 to the exponent 3 minus 1. That's 2 and 4. So those would all be the same. Just our a1 would be different. Let's check what that one would be. 3 to the exponent 1 minus 1, 0. That is 1. Okay, that looks like it's going to work. 3 to the exponent n minus 1 to cover this little 1 at the beginning here. So there is our general term for this sequence. You just look at it and see what the changes are. The kind of basic types, it could be n times something, or it could be an n squared something, or maybe an n cubed, or like we have here, some number, some base number, and that is being raised to an exponent. N is in the exponent. So just kind of see some number patterns and try to rebuild a general term and then test it and try out some things and then see what could work to build that. All right, so we will talk about two different major types of sequences, and those two types are being shown right now, actually. The one on the left, where, actually, let's write this in here for clarity. Let's think to the one on the left here. When we go from 4 to 8, from 8 to 12, from 12 to 16, what's happening at each step?
+4.
+4. 4 plus 4 is 8. 8 plus 4 is 16. 12, sorry, not 16, is 12. 12 plus 4 is 16. 16 plus 4, 20, etc. For the one on the right, what is happening at each step?
+2 +6.
Okay, so, but instead of adding, there's a different operation and the same thing's happening each time.
Getting bigger 3 terms.
Yeah, multiple by 3.
So multiplying by 3. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27, etc. So these two patterns, the one on the left where we are adding the same thing every time, is called an arithmetic sequence. Arithmetic sequence. And the kind that we have on the right here is where we are multiplying by the same thing every time, is called a geometric. Sorry. Arithmetic geometric sequence. So we are multiplying by the same thing or adding by the same thing. There are all kinds of different sequences that exist and can be made, but these two types are very common in the natural world. They actually appear a lot. So there are some useful formulas and things we can realize about them. And it's worth being familiar with these two particular special types of sequences. So arithmetic sequences first. An arithmetic sequence, as we just saw, it's based on addition. We are adding the same thing each time. And the thing that we are adding, we refer to as D. So D is a common difference between each term. So A1 plus D gives us A2. A2 plus D gives us A3, and on like that. So we already have our terms explain like what's A1 and A5 and everything. Just D is our new kind of label here thing to know. So for an arithmetic sequence, we have a common difference, which is D. So let's look at some examples and see if we can figure out, are these arithmetic sequences or not for each. So on the left here, let's look at the sequence and what is happening between each of these terms here. So going from 5 to 9, what's the difference there?
4.
Okay, so it's +4. From 9 to 13.
+4.
That's 4, 13 to 17, that's +4, 4, 4, 4. Okay, it's the same each time. Is this an arithmetic sequence?
Yes, it is.
Oh, yes. On the right here, we have another sequence. So 4, 9, 12, 17, 20, 25. What's the difference between the first two terms?
5,
plus 5. What's the next difference?
3.
3. And then the next
Oh.
one is 5 again. Next one is 3 again and 5 again. There's a very clear sequence. There's a very clear pattern to this. We know exactly what's happening. We could calculate all of these terms off to infinity, but it is not the same difference every time. So this is not an arithmetic sequence. It doesn't match the definition. Again, we care about this because we have some useful formulas and everything that can help us see various things about arithmetic sequences. So it's good to know those things, but we need to be able to first identify, do we have this special type? If we have the special type, it's the same difference every time. So the one on the right doesn't match it and is not one of those types. So let's actually look at our formula for this. So if we get, again, the special type, if we have an arithmetic sequence, our formula for a general term, probably most of you will recognize this. So general term an is equal to the first term plus the difference a whole bunch of times. How many times? N minus 1 times. So let's just look at a simple example here. A2, A3, A4, A5, A6, etc. Let's say A5. Let's think about A5 here. So we start at A1. We want to get to A5. So A1 plus D gives us A2. A2 plus D gives us A3. A3 plus D gives us that. A4 plus D gives us A5. How many times did we add D to get to term A5?
4 times.
4.
4 times. It's the 5th term, but we added 4 times n minus 1. So that's the logic behind this formula here. It's pretty simple, pretty straightforward. We just add our D thing that many times, just n minus 1 to whatever the first term is. So A1, I have the definitions here, but they're the same things we've already been talking about. Just a little quick note. Some other textbooks, when they talk about sequences and series, instead of A1 for the first term, they just might call it A. And then the actual terms, instead of A1, A2, A3, A4, they might call them T1, T2, T3. Doesn't matter, it's just a label. Our book uses these labels here, so that's what I've written for you, but I've seen other books and used other books in the past that use other labels. So just maybe keep an eye out for that. They might be different labels, but it would still be the same math. All right, there's our formula. Let's put this to use. So formula's down here in the corner if you need it. Let's say we have a sequence where our first term is 5 and the common difference is -6. Let's find the first 5 terms and also find the 21st term. So take just a few seconds here to start thinking about this, see if you can figure these out, and we'll talk about them. Okay, so let's write out the first 5 terms. What's the first term?
5.
5. They told us that. First term is 5. Okay, what's the next term?
-1,
Next three.
-7, -13, -19.
Okay, so pretty straightforward. We're just subtracting 6 each time, not anything really special going on here. So there we go. There's the first 5 terms. And they're also asking us to find term 21, A21. We could just keep doing this, subtract 6, and find out all of the terms until we eventually get to A21. But that does not sound very efficient or very fun. So let's do this a faster way. We'll just use the formula, which is again in the bottom corner here. Can someone tell us what they think A21 is?
-115.
-115. So let's check. So A formula is down there. I won't rewrite it, but A21 will be equal to A1, 5 plus n minus 1. We have A21, so 21 minus 1, 20 times D, which is -6. So 5 plus 20 times 6 is 120, but negative. So minus 120, -115. There we go. So we can just jump straight to that term using this handy formula. We don't have to write them all out. All right, let's give people a second, and then we're going to have another example with no formula shared, and you can figure it out. Okay, so next example. Go ahead. Please read and find the what it's asking. If you have your answer, you can type it into the chat. Okay, so I see people saying it is 87. So we think a 15th term, so a 15 equals 87. Let's check. First term is 3, so a1 is equal to 3, and common difference is 6, so d equals 6. We have our formula, so a15 will be equal to a1 plus n minus 1, 15 minus 1, which is 14 times our common difference. Why did I write a1? a1 is 3. Common difference, which is 6. So there are all the parts that we need, and we'll just evaluate this. If we had 15 times 6, 15 times 6, 1.5 times 6 would be 9. 15 times 6 would be 90. So 3 plus, but 90 would for 15, subtract 6, so 84. That's the way I do this in my head. 3 plus 84, 87. Okay, so that is the 15th term here. If we get the start point and the common difference, we can find any point of the sequence. So we can also do this in the other direction. We can start from two random points somewhere in the sequence like this, and then work backward to find what was the first term and what is the common difference. And based on that, what is the general term for this sequence, for any term, not just the first one? Does anyone have an idea of what we could do for this? How can we approach this problem?
We subtract the like the bigger value from we subtract the smaller value from the bigger one, and then multiply it, or sorry, divide it by the definition. For example, A11 minus A5, and the result is divided by 6.
Okay. Yes, I'm gonna write a little more detail to show people exactly how we get to that, but you got the right logic. So what we can do here, let's use the formula that we have. So our AN equals A1 plus N minus 1 times D. So this formula for a general term, let's use that here. So we have been told that A5 is equal to 19. So that means that 19, or AN, here A5 is 19, equals A1. Don't know what that is, but N minus 1, we can figure out that it's 5 minus 1, so 4. So 4 times D. We don't know what D is, but that's okay. So write my A a little better there. So 19 equals A1 plus 4D. And we can do the same thing for A11 here. So 37 is equal to A1 plus 11 minus 1, 10D. Does this look like something? When we write these two together, does it feel familiar to you?
Yeah, then just do elimination or substitution.
Okay, so this is a system of equations. We have two equations and we have two unknowns, A1, D, and D. Substitution or elimination, your choice, will let us solve pretty easily for both of these variables here. So let's do that. We'll write these with the A11 expression first. So our A11 expression, 37 equals A1 plus 10D, and the other one, 19 equals A1 plus 4D. And we don't need to multiply by anything. The A1 terms both have the same coefficient, just 1. So we'll just subtract these two. On the left, we'll get 18, and on the right, A1's canceled out, and 6D. Okay, so then D is equal to
3.
3. Just divide both sides by 6. So there we go. So we have our D term now, our common difference, and we can take this and go back into either one of our original equations and figure out what A1 will be. So let's use our A5 term. So A5 equation here. So 19 is equal to A1, mystery A1 plus 4 times 3. Okay, that's 12. 19 minus 12. A1 is equal to 7. All right, so we found A1 and we have found D, which is 3. And now we just want to find AN. What is the general term for this sequence? There isn't like a magic formula. We just kind of do some problem solving, some thinking here.
A1 plus n minus 1 times 3.
Sorry, say it one more time.
A1 plus n minus 1
Uh,
multiplied
tell me the actual term. Don't say A1. Tell me the actual numbers.
by, okay, 7 plus n minus 1 multiplied by 3.
Okay. All right. So we're just, all right. We do have this here. So we'll just use this to build it. So n minus 1 times 3, and we'll just simplify this. So that's 7 plus 3n minus 3. So that's 3n plus 4. Okay, so here's our simplified general term. Let's verify this, make sure that we are getting the right numbers. We can't use A1 here. That's something we calculated. We should go back to the original problem. So let's use this and try to calculate A5, make sure we get the right number. So A5, if we say it's 3n plus 4, so 3 times 5 plus 4, 15 plus 4, 19. Yes, the problem told us it's 19, that works. And the other one, A11, 3 times 11 here, plus 4, 33 plus 4, 37. Okay, looks like it worked. We built this general term after finding A1 and D, and it got us back to the numbers that we started with in the problem. So we've completed our circle. Looks like we have the right solution here.
Professor, I have a question.
Sure.
How did we get 19 equal to a plus 40?
Here,
Yes.
from this
and-
formula.
Yes.
Yeah, so from that's all we did. We just used this formula. In the previous questions, we were given A1 and we were given D and we were given N, and we calculated AN. But in this case, we were given AN and we are given N, but we had to calculate what's A1 and what's D. So using the same formula, just in the other direction.
Thank you, Professor.
You're welcome. Okay, so there is the arithmetic sequence, general term formula, and how we can use it. If we have any two terms of an arithmetic sequence, we can determine what the entire, like a general term is. We can figure out the whole rest of the sequence. Just how, if we have 2 points on a line, any 2 points is enough for us to build and determine the full equation of that line. Remember I said this is very similar to that graphing stuff. It's actually, that's the exact same concept. We're just kind of writing it and thinking about it a little differently. Okay. So let's go on to the next part. So that's a sequence and how sequences work and sort of a general term formula, AN formula for this. The next step is a series. A series is still a sequence, but the terms are all added together. So we have some pattern that determines each next term, but then we want to take all of those and add them together, and that gives us some information. So for example, a sequence, let's say, trying to think of a useful example. Let's say how many students there are, how many students enroll at SolBridge each semester. So new students coming in each semester. So maybe we have some kind of growth pattern. We've noticed that, okay, it's A1 for the first year, A2 for the second year. A3 for the third year, ... So we have some growth pattern. Here's what it is: the first semester, then the second semester, then the third semester, then the fourth semester. So those are individual, but with a series, we replace our commas with addition signs. So A1 plus A2 plus A3 plus A4 ... So this, as a sequence, it would tell us how many new students were there each term. As a series, it would tell us what's the total number of students. So add the students that come in each semester, and then the result, the total is, okay, the current total number of students. So that's just a basic sense of where we might want to use a series. Two things that we kind of care about with a series is a partial sum. A partial sum is the sum of the first n term. So up to term whatever, from the first term all the way up to that nth term. Excuse me. What's the partial sum? And we have a handy formula for that. And then also in some cases, we can also talk about an infinite sum. If we went from the first term all the way to infinity and we added them all up, what would we get? And it turns out that in some cases, it's just a number. It's not infinity. So we'll, not today, but in our next class, we'll talk about those special scenarios. Okay, so let's talk about an arithmetic series. We have a formula for how we can calculate a partial sum, but I want to talk with you about just sort of the logic behind that formula here. So let's try something. I have all the numbers here from 1 to 100, and we want to add all of them together. What is the sum of the first 100 numbers? This is a very famous math problem, so probably lots of you know the answer. I'm not so interested in the number, the final answer. I'm interested in the logic. What's the reasoning behind it? What's the strategy to let us find that solution? So can someone start us off here? If I want to add up all of these numbers, but in a quick, clever, easy way, what can I do?
Find the combination of the first term and the last term.
Okay, so let's start with that. So first term plus last term, 1 plus 100. That's equal to 101. Okay, what else can we do?
And then we add the second term and with the 99th term.
Okay, so our second term with our second last term, and 2 plus 99. That's also equal to 101. Perhaps we have a pattern here. 3 and 98. That's also equal to 101. Let's continue it all the way down into the middle and see if it holds for the whole thing. So the second closest numbers to the middle, 49 plus 52, that's 101. And 50 plus 51. Okay, that's also 101. So I can make up these pairs from kind of the most outside numbers, then the next one, then the next ones, and all the way down to the middle, every single pair will be equal to 101. Okay, that's a very interesting observation. That's half of the problem. What's the other thing we can do? So we notice we can do these pairs, and the pairs always add up to 101. There's one more thing that we can notice or recognize here.
Multiply 101 by the numbers of pairs.
Sorry, by the number of
Pairs, like we have 15 pairs, I guess.
Okay, by the number of pairs. So if we had 100 terms total, every term has been matched up with one other. So we have 50 pairs here. So all the way down to the fifth middle, that's 50 pairs. So the size of each pair is 101, and we have 50 of them. So just multiply those together. 5,050. That's the answer. So that's the sum of the first 100 terms here, first 100 numbers. So that's the logic. There's a more formal proof that we could write out and show that would explain this formula in a little more detail, but that's just the core logic of it. I'll skip the formal proof. So A1. So let's say we have some sequence, whatever it is, we want the sum of the first whatever numbers. That's what this S represents. Sum of all the numbers from 1 to n, whatever n is. We just take the first number, add it to the last number. So we build one pair, and then we multiply by how many pairs we have. We have n over 2 pairs. So n divided by 2. Multiplied by the size of the pair. That's it. That's all we have to do. So it's a very kind of intuitive sort of formula here. However, we don't always have a n. We aren't always given, well, some of the first 50 terms. Well, what's the 50th term? We aren't always given that. So, but we know that our general term formula, an is equal to a1 plus n minus 1 d. So let's just take this formula and substitute this in for an here, and then we get the result on the right. So we would get a1 plus a1 plus n minus 1 d, and then we just add the two a1 terms, and then that becomes this, and then there we go. So take our general term formula and our simple partial sum formula, and that will give us this slightly longer version of it, but it is the same thing. Okay, so two formulas, which really are just the same formula if you remember what the other one is. We have some examples. I'll just give you a moment to write. All right, well, let's look. So formula is down in the bottom right corner if you need it. Let's try the sum of the first 30 terms of this sequence here. Okay, let's see if we have all the parts. What is A1 here?
8.
It's 8. It's given to us. What is our n term?
30.
30, also just given to us here. An we do not have. So we could use the longer version of the formula, or we can just calculate an here. Let's do an. So an will be equal, sorry, not an. A 30 here then is a1 plus 30 minus 1, 29 times, sorry, I keep writing a1, 8. And what is our d term here? We need our d term.
5.
It's 5. So we can just see from the sequence we are adding 5 each time. Okay. So that, so 8 plus 31 minus 9 times 5, 8 plus 29 times 5. What's our number here?
153.
153. So 5 times 30 would be 150. So 5 times 29 would be 145. And then this plus 8 would give us 53. Okay, so we have all the parts. We have a 1, we have a 30, and we have n. So we can figure out this here. Sn S30 equals 30 over 2 times a1, which is 8, plus our a30, which is 153. So that's 15 times this here, 161. Okay.
2,415.
2,415. Thank you. So, we can just do some long multiplication here and figure this out. Okay, that's a 5, that's a 0, it's a 3, that's an 8, and then times this. So 161, okay, 2, 4, 1, 5. So long multiplication, we could find shortcut methods or something, but sometimes when we're doing these, we deal with slightly bigger numbers. So being able to do this multiplication kind of quickly is definitely useful. But there we go. There's the sum of the first 30 terms. We could have just done this manually in a very boring and slow way. We could have done 8 plus 13 and then take that and plus 18 and just figure out the first 30 terms and manually add them up one by one. But that's slow, that's very inefficient. Just we have a simple formula here we can use to jump to these numbers directly. Okay, I'll give you another example and take away the formula and ask you to solve them. Here we go. Please try to solve. If you have your answer, you can write it into the chats.
Okay.
Okay, it's been 2 minutes. We're also kind of running out of time, so I want to push ahead with this. I see 2 answers in the chat so far. Let's see if we get those numbers. So A1, we haven't even been given A1 here. So we should calculate what that is. Our first term, so 3 times 1 minus 4, so A1 negative 1. Our D term here, we could write this out, like we could write out first, second, third, fourth term and then look at the difference, but we can also kind of see something here. What is our D term going to be?
3.
3. Why? How do you know that?
Because when n is improved by 1 or increases by 1, the result increases by 3.
Okay, so it's 3 times n. So if it's n is 1, that this part will be 3. If n is 2, this part will be 6. If it's 3, it'll be 9. So we're multiplying by that. So that the thing we multiply by n, that will be the common difference. This -4 is just a constant that's sort of off on the side. So our D is going to be 3 here. We can verify that again just by writing, okay, here's A2, A3, A4, calculate those and just check the difference and make sure. But also the general term will tell us that. N is 50. So, okay. So our longer version of the partial sum formula, n over 2 plus, sorry, times 2a1 plus n minus 1 d. We have all the parts. We have a1, we have n, we have d, so we can just drop everything into this formula. S50 is then 50 over 2 times 2 times a1, 2 times -1 plus n minus 1, 49 times d3, 25, -2 plus 49 times 3, what is that?
147.
147. I just think 50 times 3 and then minus 3. So 147. So we're trying to do 25 times 145. Again, if I were to think of where we could just write this out as long multiplication, probably for lots of you, this is the quicker way of doing things. I kind of like my way of sort of splitting up the terms. I would think of this as 25 times 150, and then also so minus 25 times 5. So taking the 145 and splitting it up like this, 150 minus 5, and then I'd see this. Okay, so 37.5 if I take 15 times 20 or 15 times 2.5. So just put in the zeros again, 3,750 minus this is 125. And then that gives us 3,625. Whatever way you want to do it, as long as we get the right answers. Okay. So we can figure out, just from a general term, we can figure out what the first whatever terms will be. Sorry, there's always distractions with your section. There's a truck driving by selling like, I don't know, fresh squid or sweet potatoes or something. Okay, so first 50 terms, there we go. We have a formula, just find the parts, put the parts in the formula, use the formula. That's it for today. So we will do the same thing, or let's review. So arithmetic sequences, the simple type where we're just adding to get each of the next terms. We have a formula for the general term, the nth term of it. And we have a formula for the sum of the first n terms. The partial sum formula we just looked at. There's a bunch of review stuff in our textbook. So just kind of the basics of sequences, like here, look at like a list of numbers, a sequence, and try to figure out like what the general term would be, what the pattern is. There's a good set of exercises on that in chapter 12.1, 1 to 36 here. And then specifically about arithmetic sequences and series and using these formulas that we just learned in chapter 12.2, and then these exercises here. Summation notation, we'll get to that in the next class. I have a preview. I should have shown you this. So summation notation, geometric sequences, and then infinite sum formulas, and the interest application will, sorry, I dropped my pen thing. We'll probably not get to in the next class, but the class after that. But that's where we are going. The preview question for today, sorry, for next week is this. If we have this sequence, try to find the general term, then try to find the 10th term, and then try to find the sum of the first 10 terms, and then try to find the sum of, well, all of the terms. If we did this to infinity, what would happen? The infinity part might be harder, and might, if you haven't seen this before, it might take some kind of creative thinking, but just give it a shot. But the other three, just even without a formula, some manual calculation, it won't take too long. Just do that, see what happens, look at the patterns, and this is what we'll talk about in the next class. Okay. If you have questions, more questions about exam stuff or any of this or the exam stuff and whatever, just please hang around and ask. But since we're over time, I will formally finish now, and then you can ask once we're done. So thank you for listening, everyone. I will see you on maybe in the workshop that's this evening, that will be practicing exponents and arithmetic sequences and series. I've posted the questions and everything, the content that will be in that. So that's this evening. Otherwise, I will see you on Tuesday next week. Goodbye.